Now we are ready to start with this paper session, the one of 9 a.m., which is on artificial intelligence and digitalization. It's divided in two parts. There will be a first one from 9:10 to 10:30. Then we will have a break from 10:30 to 11. And we will start back at 11 with the other four presentations. But I don't want to lose any more time. We have some audience registered. Some of the speakers are online, as you can see, and some are here with me. Therefore, nothing. We will start with Ugo, which will present a paper called "A Data-Driven Approach for Asset Maintenance and Management in Power Systems." So, Ugo, the floor is yours. You can share your screen if you prefer.
Thank you very much, Regis. I guess you can see my screen.
Yes, we can see it. Let me. Yeah, we can see it.
In presentation mode.
Perfect.
Okay, great.
Thank you, Ugo.
Thank you, and thank you, Regis. And good morning, everyone. My name is Ugo Stecchi. I work for Etra I+D. Etra is a technological company based in Valencia, Spain, mainly devoted to develop technological solution for smart cities and smart energy applications. I am the coordinator of the Synergy project, and my presentation is called A Data-Driven Approach for Asset Maintenance and Management in Power System. Well, briefly, here you have the agenda of my presentation. I'm going to introduce the Synergy project with some main information about the project itself, an overview of the main numbers, of the challenges, the broad picture of what we are doing basically in this project, and some additional information on the demo site and the application that will be useful then to explain in details the tool that is at the base of my presentation. It is called, this tool, Asset Management Optimization Tool, with some information about the context, the architecture, and the feature itself of this tool, and then some results of an applied demonstration at the pilot site that we have in the project. So if I don't get wrong, I have approximately 15 minutes. It is correct to present this work. Okay, so I try to speed up a little bit. These are the main numbers of the Synergy project. It is an H2020 project under the call of 2019 Big Data Solution for Energy. We are 24 partners from 9 different European countries with a total budget of almost 30 million euros and 10 million of grant. We are in the second half of the project. We have 1 year ahead of us in order to complete all the testing and the demonstration activities. You can see here in the map all the countries, the partners that are involved in. What is Synergy? What is about? Well, it is a project, of course, in the big data area for energy application. So, as you probably know, energy industry experiences quite a revolution from an industrial business purpose perspective. There is an increasing numbers of decentralized sources that comes from renewables, new renewables and energies that are connected to the grid, but also to a new family of automation and digitalization devices that are installed at the different levels of the grid, of the infrastructures, and in the different portion of the whole value chain. That in terms reflecting an increasing complexity to control and manage all the entire system. This situation is urging some need in the field of interoperability, of course, in the monitoring and control, but last but not least, also extracting all the information for the huge volume of data that we are able to produce nowadays in the energy field. So the solution that Synergy project is proposing is creating a platform for sharing, trading, and safeguarding all the data in order to gain added value from all the legacy infrastructure, but also new infrastructures, digital infrastructure installed in the power systems. So the main purpose is, of course, to develop, deploy, and test and validate a big data platform. Here you can see a high-level representation of what the platform could be about. Of course, it is able to collect large volumes of data from different data sources that you can see here on the bottom, and through data checking jobs that we are able to collect, to ingest this data into the platform, executing this data checking job in different time frames according to the specific needs. We are not going to explain in detail how the platform is composed. It is not the main topic of this presentation, but it is worth to mention that on the top of the platform, of course, there are a lot of blocks and layers within this platform, but on the top of this platform, there is another layer that includes all the applications and the services that we have already developed in the Synergy project. In order to run analytics, as you can see here, with data that are received through the platform from the data sources, and of course this is originating some benefits due to the increasing of the data quality, the control access over all this data, and basically try to extract as much information as possible by the manipulation of this data. The project is composed by 5 different demonstration sites in 5 different countries: Greece, Spain, Austria, Finland, and Croatia. Each one of these demo site has its own peculiarities in terms of infrastructures. So we have medium voltage grid, smart building in Greece, renewable energy source and final users in the demo from Spain. Again, medium and low voltage infrastructure in Austria and smart homes applications, smart buildings in Finland, and the Croatian one is mainly devoted to the renewable energy sources. Thanks to this heterogeneous set of demonstration sites, we hope to succeed in the replication and scalability, and of course in the validation of the solution that we have developed. But going in details in the application layers that I said before, we have to say that all the applications are organized in 3 different main blocks, in 3 different tool suites. You can see here in different colors. This green one is devoted to system operators and both transmission and distribution system operators, as well as renewable energy source operators. There is another tool suite devoted for services for retailers and aggregators, the new operators in the markets, and a final one for facility management at building and district level. In this presentation, we're going to analyze a specific tool for system operators called asset management optimization. What this tool is about? Well, basically this tool is aimed at develop a predictive maintenance solution for system operator in order to predict whether an asset is going to experience a failure or not. As I said before, the smart grid revolution that we have experienced in the last year in the energy sectors has largely improved the monitoring and control actions in the power systems. And now we can say it is true that many control centers have already implemented and included in their central logic many analytics and many applications that basically bring them more higher visibility, observability of the grid, and improving the ability to perform optimal control. Nevertheless, there are still some operations that are not fully implemented, as in the maintenance case. Most of the transmission and distribution system operator still rely on traditional means that are basically preventive and corrective maintenance actions, while on the other hand, predictive maintenance solution, yes, they're quite popular right now, but mature solutions for real life and industrial application in the day by day are not so quite common. So system operators still rely on these traditional techniques. Through the synergy platform and through the possibility to have all the data from different sources available and reachable in one unique point and place, we are able to develop this algorithm, this solution based on artificial intelligence technique, images processing at augmented reality, in order to provide predictive maintenance capabilities for system operators. This is a zoom in of the previous slide, through basically just to let you know that through open APIs, we are able to retrieve data from the bottom layers, that is from the data source layers. Data are exchanged through the platform through smart contracts. So the platform is quite blind to the data that are exchanged until the smart contract is signed, and the final user of the data, that is the owner of the and the developer of the application, has signed the contract with the data owner. This allow us to have availability on the data, both historical and real-time data, according to the what is signed in the smart contract. And based on this data, we have developed our solution. Going in detail in the description of our solution, here you can see high-level architecture of what's inside of our tool. On the top right here, on this gray box, here you can see the two main building blocks of the tool. The tool, I remember, it's called asset management optimization. Two main actors are asked to upload the data to be fed in this application, that are the distribution and the transmission system operators. The tool is composed, inside the tools there are two main building blocks. One is called network asset health estimator, and the second one is called network predictive maintenance tool. In this architecture here, you can see mainly the structure of the tool itself, how these two building blocks are communicating with the core of the platform. Into the core of the platform, we run the models, and on the top layer here, you can see the data that we use to feed the algorithm. We use basically pictures from asset. Pictures can be both acquired manually from operator or from security cameras generally installed in substations or in critical assets in the power system. Measurement acquired from manual inspection in case some specific measurements is performed by operators in the field, and then also data, all the data from SCADA, so all the measurements and logs that the SCADA is able to acquire, and then of course all the historical records. The two building blocks here are devoted, basically the first one that is called network asset health monitoring is basically devoted to the augmented reality visualization, the visualization of the asset health, so the state of health of the asset that we have in our pilot site, the visualization of the metric and the analytics of the picture that we are able to acquire. On the other hand, there is the network predictive maintenance managers that calculates the early alerts failures and help the personnel with the prioritization of maintenance task. In going in details of what's inside each one.
Sorry, Ugo, 5 minutes left. If you
okay.
Thank you.
Thank you for the reminder. At the basis of the first one, the first one building block basically perform the picture analysis and then also has classification models that is able to calculate basically if an asset is going to fail, and another regression model that will predict in how many days the asset is going to fail. These are the features that there are in the in this block. Basically, the two main calculations algorithm are based on long short-term memory neural network. All the characteristic and the number of neurons and the loss function you can find in my presentation here, but we have basically use a classification neural network for the asset health score calculation, and the regression neural network for to predict in how many days the asset is going to fail. The other tool basically perform an analysis of contingencies, and it is able to say whether after a failure there is a cascading event. So another failure, it will be it is likely occur in another asset. We have applied this well, there are also some training workflow and probability another work for calculating the probability as soon as we acquire data from the in real time from the demo site. We have applied this tool in the Greek demo site, so in a portion of the distribution network with the medium voltage overhead lines and medium voltage power transformers. We have 46 power transformer and 21 overhead lines. We are able to calculate the state of health, so the probability of failure in this time horizon here, 30 days, 60 days, 90, 120 days. We use 3 years historical data to train the models, and you can see a screenshot of the graphic interface with also some map to include georeferenced tag of the considered assets. And of the 67 assets, sorry, we have identified 2 of them with a higher probability to have a failure in 30 days. Also, that correspond actually to a particular portion of the grid identified by the system operator with the highly stressed conditions. Field on the measure have confirmed that these two assets are going to experience some kind of outages, while overhead lines or early alerts have detected no incipient failure. Also, there is a mobile application for the field operators. Here you can see some screenshots of the tool itself, with the probability of failure for these two considered assets that have witnessed the higher probability failure in 30 days. I have to cover the name of the asset for privacy reasons, and here you have the score in accuracy for the classification model, and the mean square errors is equal to 2.5 days for the regression model. And this is the main conclusion of until now, until the first 6 months of testing in our demo site. We have confirmed that our algorithm is able to predict outages, and in a portion of failure of grid where incipient failure are likely to occur, as confirmed by the system operator, and to support in the meanwhile this transition towards a more digitalized operation of the grid for the system operators. And this is the conclusion of my presentation. Thank you.
Thank you very much, Ugo. I can see that you have your all your social media in here. So for people that want to take a look at them, you can leave it here for a second. I just want to remind that there is the question tag on the right of your screen. So if you want to make a question, to ask a question to Ugo right now or later, just use this chat for commenting.
Okay, I have to stop sharing if I have to see the question box. Otherwise, I cannot see it.
Yeah, but we will. I mean, I will reply to the questions for you. I mean, I will tell you the questions that will arrive.
Okay.
Yeah, please stop sharing the screen, which is fine. Thank you very much for your presentation. I think it's a very useful tool for DSO and TSOs, and the fact that you were able to find out that that could have been failures in the future in 30 days. Like it's very useful also for the system operators. I'm curious to know if then they applied some maintenance procedures in advance after that you told them that there was this possibility. So I don't know if it already happened or not.
Well, of course, the full application of such kind of tools require a deep renovation in the industrial operation, in this case of maintenance operation. So you have to reconsider all the procedure on how the maintenance and management of asset is organized in your company. Of course, we cannot move until this stage because it is an activity inside the organization of another company itself. But for now, I can say that field measures, of course, after these results that have been somehow repeated quite times after we came up with these first results, the DSO in this case have performed some specific monitoring activities in the field and have witnessed some critical measurements in that nodes of the grid as over temperature, other things like this, or other conditions that may have led to a potential failure in this identified equipment.
Great. Yeah, I hope that it can help them also in the future with other kind of measurements. And I guess it's very difficult for big companies like DSOs and TSO to like change all their maintenance procedures and maintenance schedules. So it will take a while, I guess, for them to take the habit. But yes, thank you very much.
I agree with you.
But yeah, we will see in the future. I mean, in the next minutes if some question comes, and we can take them in the end of this session if you're okay with it.
Okay, thank you.
Okay, thank you very much, Hugo. Okay, now we pass to the next speaker, which is Salvador. He's presenting for the Universidad Politécnica de Madrid. So please, Salvador, go ahead with your presentation. Share your screen if you.
Okay, perfect. Yeah, I'll start sharing my screen. Can you see my screen?
Yes, you can go in presentation mode right now.
Okay.
And that will be perfect. Okay, thank you very much.
Okay, so shall I start? Okay, perfect. So I'm Salvador González Gerpe, and I'm going to present our paper that is called An Extension of Theme Descriptions from the Web of Things for Digital Twins. This paper is based on the COGITO project, that is an European project that I'm going to talk about later. First of all, I'm going to talk about what are the digital twins. So a digital twin is a virtual model designed to accurately reflect a physical model. In this case, for the COGITO project, we are going to use some data that in this case is going to be, for example, 3D models, scheduled data that are like tasks or something like that, workers, and resources. All of these data are going to be acquired by sensors at the physical model and will be sent to the virtual model to make the processes that it has to have, like simulation or something like that. And once the process have been made, it will be sent back to the physical entity to make the process work. Next, I'm going to present the COGITO project. In this case, the acronym of COGITO is the Construction Phase Digital Twin Model. These are the COGITO project partners, that in this case, we are from the Universidad Politécnica of Madrid, and the other members of the paper are from the UCL, the University College of London. And all of these type of digital twins are going to be made on the 3 pilot sites. In this case, there is one in Austria, another one in Denmark, and the final one in Spain. As we can see here in this image, we can retrieve information from satellite images, 3D scanning, aerial vehicles, weather, 3D geometry, scheduling, budget cost, and some of other data. And this data has to be preprocessed in a construction phase digital twin platform, where the data has to be linked to perform a lot of applications like the health and safety application, quality control, adaptive workflow management, and the UI, GUI, and support apps. In this case, all of this linked data is based on open standards like the semantic web W3C, that is, for example, the old RDF and Sparkle. The ontologies used are also open standards like SARE from Etsy, Bot, and Brick. And finally, we are going to use the Web of Things, that is a part of the Internet of Things, to provide more information to the processes of the digital twin platform. So in this project, we propose 3 principal challenges that happens due to the data that we are pre-processing and translating to linked data. So the first challenge is the lack of semantic interoperable data due to the heterogeneity of the APIs of the physical layer. This is why we have a lot of heterogeneous data that is processed in the physical model and has to be linked to make it semantic interoperable. All of this data has to be translated by a specific tool. So that's why we proceed to get the second challenges. That is the difficulty of orchestrating the translation services of the semantic interoperability approach. Because as I said earlier, we need one specific translation tool to translate one specific type of data format of heterogeneous data to semantic interoperable data. And why we have also a third challenge. This challenge is also the complexity involved in managing the COGITO related data for grouping it into digital twin processes within the digital model. This is why we have a lot of data, but there are no groups of what are the processes, specific processes that has been made inside the physical model or in the digital model. As a solution to these problems, we can see here 3 parts that has all the data that we process in the digital twin. In the first case, we have the 3 different, for example, resources that are, for example, the construction site in IFC format, the schedule elements for in XML format, and also the resources in CSV format. So we can have all the information in different files. But in the second level that we are using in the digital twin platform, we are storing all of these elements instead of only in files in a database where we can get all the information about the construction sites in IFC format, the schedule in XML, the resources, the workers, etc. But we have gone one step further. And I'm going to explain this by 3 simple questions. The first question is, how can we retrieve information pertaining to a worker who works in a certain place, who perform X task, and needs a specific resource to achieve it? We solved this problem translating all of this information at the databases to RDF format, creating the digital twin knowledge graph. As we can see here, we have the construction site in RDF, the schedule, the resources and workers, and all of this data are on RDF and also are linked. The second question is, when we have to translate heterogeneous data into semantic interoperable data, how can we know what is the translation tool we need to to make the correct translation? So that's why we create the second knowledge graph. That is the translation service knowledge graph. Here in this graph, we are going to store the information about all the data types that we have to translate into in the semantic interoperable data, and the links to each tool to translate it correctly. And finally, the third question is, if we want all the information referred to a specific process of a digital twin, how can we acquire it? That's why we create the third knowledge graph, that is the platform knowledge graph, where we are going to store all the information about the links to the data in heterogeneous format, that is, for example, on these databases, and also the link to the information that is in semantic interoperable data, that is here in the digital twin knowledge graph. So that's why we can perform the specific process into the different processes. So as we saw earlier, I'm going to start explaining challenge by challenge. What are the problems? The first challenge was lack of interoperable data, that it hinders, limits, or cancels the exchange of data between different applications. Also, data do not have any kind of meaning because it is heterogeneous data. And also the data has no information that describes and references them to each other. But you are going to ask, what is interoperable data? Interoperable data, it's the ability of 2 or more systems or components to exchange information and to use it, the information that has been exchanged. But you are going to ask again, what is semantic then? Semantic is the portion of the interoperable data that gives meaning to that information and also refers them to each other, as we can see here in the meaning and here in the reference to each other. As a solution to this problem, as we saw earlier, we create at the knowledge graph generator, for example, the translation tool per that data format. And here we are going to use a pre-processing and the translation using a specific tool that is called Helio, that use mappings to produce standardized data, standardized by the COGITO ontologies that we create also. These COGITO ontologies are also standardized by the ontologies that we saw earlier. Once all the RDF file is created, we just validate it and send it to the digital twin knowledge graph. Here we have, for example, the links to the COGITO ontologies and to the Helio tool. And here we can see an example. For example, the construction site with IFC format, the schedule in XML, the workers in JSON, and the resources in CSV. And all of these files are going to be translated by its translation tool, getting the RDF. In the second step, we are going to give the RDF to the validation tool using Suckle shapes, that is a type of file to validate RDF, to validate it. And in the next step, we are going to send the validated RDF to the digital twin knowledge graph that is going to be stored here. The final step is to link all the RDFs between them. That's why we create also the tool that is going to link all the graphs between them. The second challenge is the orchestration translation services. That is why data is expressed in different formats, so cannot be translated into interpretable data using any type of translation services. So it has to be translated with a translation service tool that is compatible with this type of format. And also we have another problem, that is the increment of different types of data and formats that can be unmanageable, because we can have, for example, 1 million of different type of formats, and we have also to have 1 million of translation services tools. So that's our problem. As a solution to this problem, we have the decentralized system orchestrated by theme description. That the theme description, I'm going to explain it in the next slide with an example. In this case, we create a tool that is called Theme Manager, that is going to be the responsible of getting the file format and the data type, and is going to see what is the translation tool that it has to use to make the translation. So as we saw earlier, the Theme Manager is going to take the format, the data type, and is going to ask for the translation service knowledge graph that has to be created previously. And it is going to retrieve a theme description that in this case is a semantic description containing all the function and information of a particular thing, as well as the accesses to it. So this thing is going to be the different translation tools. In this case, for example, the theme description contains all the links by data format to the specific translation to make the correct translation to semantic interpretable data. As an example, we can see here that if we have the IFC construction site, we look for the theme description that contains the format IFC and the construction site as a type, and the link is going to be this one. So we have here the arrow to the knowledge graph generation, that in this case is the construction sites in IFC translation tool. And this is the same example for the schedule XML with the format type link, and here is the translation tool. Finally, for the third challenge, we are going to manage all the data that we are using inside different processes. So what's the first problem? It is complex due to the amount of data available in terms of finding specific data. Second problem is the provenance. If the heterogeneous data is needed, there is no link that reference to the information once the information is translated to interpretable data. And finally, the data is not referenced to a particular process, because we have all the information in databases, in knowledge graph, and all that, but there is no exact information for one specific process. So we have to associate it to it. As we can see here in the solution, when we have, for example, an IFC format with this data type, the theme manager is going to be the same process as we saw earlier, and the data that is passed for the theme manager is going to be stored in the construction site database. The RDF produced by the translation tool is going to be stored in the digital twin knowledge graph, and also the theme manager is going to create a theme description, storing it in the platform knowledge graph. How we can create the theme description? So the creation of the theme description is the data linked from the data information, that first of all is the identifier and the description of the file. Next, we are going to have the link to the heterogeneous data, that in this case is the data that we store in the construction site database. Thirdly, the link to the semantic interpretable data, that in this case is the RDF file that we got from the translation tool, and it is stored from in the digital twin RDF. In the digital twin knowledge graph. And finally, we have to link it to the process theme description that is already created in the platform knowledge graph. So here we have an example of the digital twin process theme description that has the link to all the related interoperable data that are under this process, and also the links to each theme description that contains the information, for example, for the construction site or the schedule. And we can see here the link to the construction site theme description that has its identifier, the description, and the link to the interoperable data and the heterogeneous data. And also for this schedule theme description that has the XML interoperable data and the XML heterogeneous data. Finally, the conclusions. It has been handled lots of data from the digital twins. Also, we created a semantic interoperable approach to handle the problem of describing and changing information between different systems. And finally, we manage and orchestrate the data between internal digital twin tools, as for example, the translation tool, as we saw earlier, with the option of managing all the data but by digital twin processes. And that's all. Thank you for your attention, and that's it.
Thank you very much, Salvador. Is there any question from the audience here? Maybe yes, there is one. Yes.
Yeah.
Yeah, you can try to speak loud, or you can come here as you prefer. Yeah, Salvador.
Mm-hmm.
The question is coming for you.
Hi, Salvador.
Hi.
I am Pablo. We were together this summer in Cercedilla.
Yeah.
What is because I see you are representing the IFC file, the workers' schedules, and what is the other one? Operations processes, I think. I don't know. Well, what is the objective of the digital twin? To manage the construction processes in the building?
Yeah, to manage all the processes, as for example, the workers has to construct the railway station for the COGITO project, and all of the processes that are there in the construction has to be monitorized by, for example, the movement of the worker, the resources that it takes, where it is allocated in the IFC, for example, the 3D model, and that's all.
So so the digital twin would be like a tool to know, like in real time, how the construction process is developing. Is right?
Yeah.
Okay, and you can do that by the web, by different partners, perhaps in an open platform, I would say. Yeah. Okay.
Yeah, one partner that create the information from the physical model, and once we get the information from the physical model, it will be sent to the digital model to make the exact reflection of the physical model with all the processes and in real time.
Okay. Thank you.
Thank you.
Salvador, maybe another little question, because you said that it's useful, the digital twin, for the construction phase, but do you plan also to have it involved with the real-time data during operation, and so provide, for example, simulation for predictive optimization, or it's just for the construction phase of the of the building or the fair? Yeah, exactly.
No, we can use it for also managing all the simulation of when the construction just finalized. The digital twin can be also used to make the managing of all data, the simulation for future, I don't know, problems in the system, and I don't know, something like that. That's solving problem issues. Yeah.
So this will add a layer of difficulties in your work in interoperability, I guess, no? Or the all the translation are already done for of the data format are already done also for operational data. Okay. Thank you very much, Salvador.
Thank you.
That's it. If there are other questions, please write them on. I mean, from the audience, write them on the in the section on the Hopin tool. please. And now I think that we have, we have Çağatay. So please, Çağatay, were you able to? You can stop sharing the screen, Salvador, please. Thank you. Yes, you are able now.
Yeah, I'm able.
Yeah, that's
so
perfect.
Just I want to be sure that I'm on the right screen. Do you see it clearly, or?
We don't see it in presentation mode. We see the one with your notes. So you can go on.
Wait. What about now?
Now it's perfect. That's correct.
Okay. So can I start?
Yeah, please go ahead, Çağatay. Thank you.
Hello, everyone. This is Çağatay Yılmaz. I'm from Turkey. I'm representing Lande. I'm the innovation manager of Lande. Lande is an ICT solution provider, and I am also the project coordinator of Eco-Qube project, the artificial intelligence augmented cooling system for small data centers project, which was funded by Horizon 2020 program. So I will try to make it simple, and I will try to explain, give you a glimpse of what's happening in the market and how it's going to affect us. I should start with European Green Deal, but our studies started way earlier than the Green Deal because the market started to take some actions to be more energy efficient. So when we started this, we wanted to reduce the energy consumptions, especially for the cooling systems. But on the way, EU introduced us the EU Green Deal, and they said, okay, guys, like we're going to make EU a climate neutral continent by 2050. But wait, for ICT and data centers, we have to make it earlier because ICT and data centers, they are really power hungry and their carbon footprint is rising rapidly. So the goal to make them carbon neutral is 2030. This is a bold statement that we have to act together. So Eco-Qube is a result of this endeavor. So what is the challenge and what is the state of the art technologies in the market now? You might not notice it, but we moved to cloud. We moved everything to cloud. And during this moment, there are some technologies. To be honest, I love cloud. Everybody loves cloud. But there are some technologies, they require a bigger, a wider, broader band and a lower latency. Consider the fact that if you run an Industry 4.0 application, or if you set up 5G networks, you need this lower latency and you need broader bands, which requires pushing the data centers to the end user, which means that there are some hyperscaler data centers in the world that we most of the times we put the cloud there, and there are end users, and between them there will be some scales of compute and storage. They actually change. They change from a few kilowatts to hundreds of kilowatts. And these pushed IT systems, usually they are being run by not so professional stuff. So from right to left, we work with, in the hyperscale data centers, we work with professionals. They know what they are doing. They know how to keep the IT systems up, but they also know how to make it efficient. But on the left-hand side, we usually work with some IT managers. They only care about uptime, but they have less information about the efficiency. So in this phase, from far edge to on-premise IT devices, we have to support them, and we have to make it in an efficient way, and in an automized way that the system would work. So what are the problems right now? I'm a physicist. I didn't know about the IT systems at the beginning, but it's obvious that we are not listening to IT devices. And all the subsystems in the data centers, from the IT systems, virtualization layer, cooling systems, and energy systems, they all act individually. So this is the biggest problem, and there is no holistic approach. Like the software layer and the hardware layer, they are also working independently. So we believe that this is the biggest challenge in front of the data centers' energy efficiency. So we also acknowledge that the hyperscalers, I mean, all the existing technologies, they were developed for hyperscalers, so we have to make them a bit more edge-friendly, edge computing friendly. So what we are doing, first of all, we listen data centers, which means that we are trying to collect, as the other presenters mentioned, we have a bunch of data, and this bunch of data are usually not used well. So we acknowledge that the existing data center infrastructure management systems, they help, but they have to be smarter. They have to collect the data, the big data, and they have to interpret it in a better way to make it useful. So also, market was dependent on some KPIs, which are useful, but not giving the big picture to us. So what we said, okay, we're going to listen to the data centers. We are not going to, for example, for cooling, we are not going to be dependent on some thermal probes, but we are going to collect the IT devices data and be sure that we are cooling well. Then we're going to control the cooling system and the IT system in regard to this big interpreted data. So to be able to make it, we had to actually bring together the IT infrastructure and the other infrastructures in the data center to connect them into a separate layer, separate and secure layer. And once we make it, we start getting the benefits of the big data. And we call it an environmental data agent, and this environmental data agent at the end of the Eco-Qube project, it's going to be open source. It's not going to help all the data centers, but at least it's going to be a good start for the data centers. So what I mean, once we finalize this, once we develop the future of the data centers, the end users with limited capabilities, they will be able to see what is really happening in their data centers. They can actually compare the workloads. They can understand their real cooling facilities, cooling capabilities, and they are seeing actually in which sides of the data center they fail, especially about efficiency, and in which parts of the data centers they succeed. And most importantly, since I told that this people need some support, or artificial intelligence augmented system will support them to kill everything unnecessary in the data center, stop the zombie servers, idle servers, gain some efficiency from there, and hopefully in a three-dimensional thinking way, move the workloads into a limited part of the data center and control the schedulers like workload or orchestrators and the cooling in regard to that, which obviously, hopefully, is going to end great energy efficiency gains for data centers. No, almost. And finally, what EU especially wanted from us to limit the usage from the utility grid, which obviously has a higher carbon footprint, and integrate the data centers more into renewable energy sources and batteries. Once we are capable of making this, our energy carbon footprint is going to reduce for the data centers, and we're gonna benefit from the buildings and districts heating and cooling systems in a way more better way. So this is an ideal world. This is an ideal world that, sorry, I'm experiencing some open office issues. I have to change the place somehow. Sorry. So what I was telling, this is a really important approach for edge data centers and how we have to manage them. We have to integrate them into buildings in a more efficient way. So I want to give you some examples from our pilot data centers. EMPA, Nest facilities from Switzerland. They are a great example of a microgrid, an ideal microgrid. And we are testing our approach in Switzerland. And why they are so important? Because their system, sorry, let me start from here. EMPA in Switzerland, they consist different cooling and heating pipelines within the data center. This is basically what we expect to see in hyperscale buildings, and this is how we in the future how we can integrate small edge computing units to the buildings. If I go back, what we have done, obviously we support open science and we integrated an open source hardware compute unit and an open compute project unit into these facilities. This unit is totally refurbished and it's in compliance with the European Commission's Circular Economy Action Plan. And this unit is capable of zonal cooling. And this zonal cooling is benefiting from the building's cooling unit, and it's capable of cooling the data center differently in different zones. And also this unit is capable of catching and reusing the waste heat from the data centers, and it is sending to the building's heating system. So this is a small unit, but the results are going to be scalable, and we're going to be distributing the results until the project ends. So what we are trying to do here, we are trying to exchange our experiences to the ESHRE standards, because as ESHRE trying to enhance and raise the inlet temperatures of the data centers for higher efficiency, we are also trying to give them a glimpse of information, how to make it, what are the best temperatures for energy reuse and the best cooling. This is also important because we care about uptime. We don't want our IT systems to stop. And if the building's cooling system fail, and this is a study case that we experienced during an electricity cut, the IT system's efficiency and their cooling stops too. So what we are trying to do, we are trying to mitigate the risks of which is coming from the building, because if you connect the IT devices to the buildings and districts, you also you should mitigate the risk from the IT device and district systems together. So this is going to be another outcome from Eco-Qube project to guarantee the uptime and raise the efficiency together. Another pilot that we try our technologies is block heating from Netherlands. Block heating is a new startup which is also aiming to minimize the carbon footprint of the IT infrastructure. They use open compute project equipment because it is open source and it is upgradable, and they use cold plate technology to catch the waste heat from IT devices directly, which is giving them a capability of lowering the PUE to the market-leading designs, and this is a really easy and efficient way to recapture the waste heat. So what we see from our first trials in block heating, in the lower IT loads, we generate some waste heat, and which is giving us still good power usage effectiveness ratio for the market, but our energy reuse factor is slightly lower. But once we actually reach the medium and high IT loads, we capture most of the waste heat, and our power usage effectiveness ratio or efficiency is skyrocketing. So this is something that we have to consider while developing the future sustainable buildings. So altogether, we are working with 11 partners from Europe. So I strongly recommend you to follow us and to be able to see what else the advanced energy efficiency measures we are going to introduce to the market. If anyone wants to reach us, these are our email, web page, and our Eco-Qube newspaper. Please follow us, and I think this is going to be the end of my presentation.
Thank you very much, Çağatay. Very, very, very interesting. So, is there any question from the audience? And if not, I have one, which is a basic one, I think, but it is of my lack of knowledge, so I will ask you, probably you know it. Do the source of heat, so the data centers, need to be close to the other user that you want to reach? So, for example, the greenhouses in the second case, and the buildings in the first one, or I mean, this is a requirement, or for developing the solutions that you are developing, or it is not?
It depends on the place and the technologies, obviously, but if you are closer to the end users, the losses from the heat transfer is going to be minimized. So since we are already working on some modular data centers, which are easy to be placed anywhere, I would suggest keeping them as close as possible to the end users. I mean, both in IT side and both in the waste heat valorization side.
Yeah, no, this makes totally sense. I was just imagining a big data center close to a group of greenhouses. I wasn't figuring it in my mind, but yeah, since they are modular, that's true that they can be put like very close to all kind of end users.
I should also mention that, like, the temperature of the return, water, or liquid, is really important for waste heat reuse. You know, if you can't reach some certain temperatures, it's really difficult to reuse the waste heat in a commercial way. So also in this case, a greenhouse is a great example, because you can be a bit more flexible about the return temperatures, but depending on the usage, I think the distance is going to be more critical than ever.
Okay, thank you very much. And if any other question will come in the chat, I will let you know. Okay.
Thank you. Have a nice day.
Thank you very much. Thank you very much, Çağatay. Okay, we pass to our last presentation of this first part of our session. So I invite Dimitrios to join me over here, which is our first physical speaker over here, and he will talk about the automation of building energy model calibration for improving operational efficiency in buildings. Okay, I will just find the presentation, because we put it here. How can I go on the main screen now? Okay. So we have it here. It's iBECOME. Okay. Let's see if it opens it. Okay. Now I will go on the others. Wait a second. Okay. Go here. Sorry, huh? Let me just see if they can see it now. No, well, let's see my screen.
Entire screen.
Yeah, wait. Okay, wait a second, please. Entire screen. Yes. Now. Okay. No, now it's fine. Okay.
Perfect. Thank you.
Dimitrios. Thank you very much.
Okay. First of all, thank you all for the great presentations, and thank you for being here. I'm Dimitrios Ntimos. I'm working with IES in the R&D department as a project manager of R&D projects, and I am coordinator of iBECOME. So today I will present you an introduction to IES, then a quick intro to iBECOME and our main role there, where the problem we're trying to solve, that is to use calibration of building energy models in applications in the operational phase of a building. And I will conclude with how we are trying to do this and our findings through iBECOME project. For ones you don't know IS, so we are developers of recognized software for building environmental analysis called the virtual environment, and that is mainly using building physics and doing full year dynamic simulations. And through our participation into R&D projects, we managed to further develop and expand to digital twins, not only for buildings, but also communities, and trying to tackle the pretty much known problems that there are there. Just switching quickly to iBECOME. So now iBECOME is a AIDS 2020 funded project. We're a group of 10 partners from 4 countries in Europe that our main goal is to reduce bills in a building or facility through energy savings and demand response, while we improve occupant well-being and optimize comfort, thermal, visual, and air quality by leveraging IoT, data analytics, and efficient control of the building HVAC systems, while we in parallel enable additional services such as EV charging optimization. So looking a bit deeper into our proposed solution is that on the left-hand side, you see the building hardware, the IoT, where we connect to smart sensors, thermostats, or any other devices through any protocol to a hardware that's called automation server provided by Schneider Electric that is capable of collecting all the data both ways, like a two-way communication, and exposing it into the right-hand side, where it is the cloud, the enterprise server, again by Schneider, well-recognized software as well. And through API connections, we managed to take all the data, historical and live data, analyze it, make predictions, calibrate energy models, and inform the users through dashboards or sending back to the hardware like set point values, it's better, or schedules for operation of, let's say, a thermostat. So our role in IS is mainly on the right-hand side. We start from the data from the building, we analyze it, we make predictions, and we try to optimize the energy use while not compromising comfort. And that's where the challenge comes, and that is the reason of this presentation today. So in iBECOME, we have these services that we hope to demonstrate in the next year. And in a nutshell, energy comfort optimization, measurement verification, demand response, fault detection, diagnosis, predictive maintenance, and what-if scenarios are our core services. And additionally, we have healthcare management for a care home for the elderly, EV charging optimization, and car sharing for the employees of a building. So it's quite challenging, quite a lot, to be honest. So now, I'll focus on energy comfort optimization mainly, and measurement verification and what-if scenarios are the ones we're capable to do using building energy models. So how we do this? So now we combine physics-enabled simulation with the real data from the building and with AI and machine learning to have all the benefits from the physics simulation, from data-driven simulation, and also fill in the gaps and anomalies using machine learning. So this way we come up with a performance digital twin from the operational phase of a building. So now usually we see this kind of approaches, mostly data-driven. So now we wanted to be able to use the physics-based simulation engine we have in IES, but it's not on the cloud. It's a desktop software, which is quite useful because it's used to predict of future energy savings, to estimate of achieved savings, so that enables energy performance contracts and measurement verification. And for the optimization of energy use and comfort is useful as we generate virtual data sets. We can simulate operational energy conservation measures and push those strategies, that the best ECM that we simulate, to a device. So it's quite useful to be able to predict the future condition of a building. So usually now in building simulation, we start with what we call like a baseline compliance model. Is what you do to get the permission of a building permit, basically. So it's a basic model. And what we want to reach on the right-hand side is the operational model, and the process called building energy model calibration. As you see at the bottom left, the green curve is the energy consumption that is simulated by the basic model. The red curve is the metered, and the blue one is the operational model. So you see that we reach a very good accuracy of predicting the actual performance of a building through calibration. But if we were using the basic model, we will be way off in our calculations for the operational phase of a building. So now, how we achieve the calibration? There are many methods, and there's not a standard process like in the literature or in the industry. So it's usually a lengthy and manual process of trial and error that requires expertise, requires an expert energy modeler to undertake, and usually in a desktop computer. So there are many methods. These are just screenshots that I've seen all these years in research projects, or generally in IES where I work. So there are quite a few spreadsheets, tools. So we tried to basically unify them and put them on the cloud. But first of all, we had to choose which calibration methodology is the best for us. So we made like a short literature review of some good calibration methodologies. And we came up that the whole building optimization is good accuracy, medium complexity, and medium computational effort. And what we want here is accuracy. So comparing to, let's say, profile optimization, which is low complexity, low computational effort, it's not good in accuracy. So we had to compromise and go with medium computational effort and high accuracy. So as I mentioned before, calibration is a complex problem. We had basically two main problems to solve. One is that one that requires relies on the user knowledge, past experience, statistical expertise, engineering judgment, and an abundance of trial and error to achieve building energy model calibration. That's the first problem. The second is that our core software, the ISVE, is a desktop suite of interconnected tools. It's not just the physics simulation engine. So we had to extract it from the platform, the desktop suite, and cloudify it. So that's what we call decouple. We call it Apache simulation engine, to decouple it and put it on the cloud, and also make it as a lightweight tool to avoid having too much computational effort on the cloud. The plan B would be to use a reduced order model, which is a simplified version of an energy model. However, again, we would lose a lot in accuracy. So we decided to go with a full simulation engine, a lighter version, to be able to work on the cloud. So all this, we came up with a web tool that has a user interface, as you see on the right-hand side, and an API, so that enables both humans and machines to run physics-based simulation on the cloud and perform calibration. So it also includes tools that automate many manual steps that are required by an expert in the calibration process to reduce the time and it also improve the calibration accuracy. So very quickly, in a schematic form, our current calibration process starts from the left, that we use model assumptions and anything we can collect in data from the building, like weather data, measured data, or if we install sensors or existing sensors and meters, we collect to our simulation engine and iScan, which is a tool for that reason, to collect all the data from the building and the weather data. We come up with the first baseline compliance model. Then we follow this iterative process inside the box that is to achieve calibration and come up with what we want, the operational model. So that's a manual process you see in the first circle. So what we achieved is to be able to automate the manual steps required in the iterative process. So now this tool includes quite a few tools. So it's you upload the building model, you press a few buttons, select a few options, and it runs many simulations automatically, performs sensitivity analysis, calculates calibration metrics, and optimization to find the best parameters to use as inputs to your model. And it can be used as an API from a client, generates a calibration report, and can be exported. The results can be exported to CSV, to our own software, iScan, or again, an APR file, which is we used as a compressed energy model in this form. That can be translated to other open source formats. And yes, finally, I just include the screenshot of the API we have for the calibration on the cloud tool. So now we have this so that it can be triggered automatically. We can schedule this to perform calibration whenever it's required. So if the tool can check if there is a need for calibration, because it collects the latest data from the sensors. And if there's a need, it can trigger recalibration. So we tested in a case study this tool. It's a warehouse building in Bologna, in Italy, and we created from the data we collected the energy model you see on the right of 2 rooms. And just quickly to say that we compared a manual calibration with the automated tool, and we found that our automation tool achieved 27% improvement in calibration accuracy. And the key message to take from this table, I hope the slides will be available after, so that someone can read on their own pace. So the key message to take is that manual calibration for this model required 2 days to complete. The automated calibration required less than 20 minutes. So it's quite important improvement. And of course, reducing the reliance on the expertise of the model. So now using in action the calibrated model that we theoretically achieved is we enabled to be able to interact with the calibration in every time step with data-driven algorithms. So this is like a combination of physics-based and data-driven. In this way, we can make predictions using an intelligent controller that is based on artificial intelligence. And as a sample workflow, so we collect the data that we need to come up with a model manually and from the IoT and DMS of a building. We develop the baseline model. develop the initial calibration semi-automatically and upload it on the cloud. And then we schedule these co-simulations daily or hourly, whatever is needed. And we let it run the control algorithms and calculate the best control strategy, for example, a heating thermostat. And it sends to the dashboard, or if there's capability, or to the device directly to change the heating set point or schedule. So, and then we check regularly if our model is calibrated so that we generate accurate results and perform. That's the step we want to introduce and test now, to perform auto calibration of the cloud and inform user to check. So some first results we had in simulation, not in an actual building. So what you see here is on the x-axis are 2 full days. On the y is temperature, cost, and kilowatt. And the 2 lines are the upper thermal comfort limit and the lower inside an office environment, like an office room. And the red one is the energy price. So we take into account the energy price as well. And we try here to calculate the best set point to avoid violating comfort, also achieving the lowest prices in parallel, and generate energy savings. And so this shows the temperature in the room with our solution. As you see, it keeps within the comfort band, and at the times that there is a high energy price, it reduces it shuts down. So and it's also an algorithm that's based on reinforcement learning technology that is continuously learning and self-improving. And this yellow line shows the sensible load, the energy use, basically. So as you see, for example, when the energy price is high, it goes the lowest energy use that it's possible. And comparing to this method, the RL control, to other 2 solutions, that one is the maximum comfort, so that we want to have the maximum comfort for this zone. On the left is the rule base, so it's just a rule, let's saying, for example, that I set my temperature to 22, or there's a rule in between. So the rule base was the cheapest one, but violated many times the comfort that we set, the comfort, but so it went up or lower than the comfort that we require. The maximum comfort was the most expensive that we tested, and in between is the RL that achieved 25% lower energy cost comparing to maximum comfort, and did not violate the comfort rules we had. So this solution is going to test in 4 buildings, 2 smaller, 2 larger. The smaller ones did not have any energy retrofits and no BMS installed. The other ones combined both. And that's what we're going to do in iBECOME the next year. And in our website, you can find our public reports. And the second one is describing in detail what I presented to you today. And as a summary, again, the calibration is quite complex, and we're trying to find solutions to simplify it and use it in the operational phase of a building. And yeah, we will trial our service in the demo sites and evaluate them. Hopefully, this time next year, I will be able to present to you what we achieved. And I think that's it from my side. Yeah, you can stay tuned, follow us on our social media, LinkedIn, Twitter. And yeah, if you want to follow our progress in the project. Yeah, thank you.
Thank you, Dimitrios. Are there any questions from the audience here?
Yeah. I was wondering, when you do the step, so the initial automatic calibration step that you come out, it seems, with a reduced order model directly with the parameters, is that model still physics-based, or is already just statistical
Basically, we don't use a reduce order model. We had to do a choice either to use a reduce order model because it's lightweight, or try to extract the engine from the platform we have for environmental analysis. Inside there is a physics simulation engine, so we managed to decouple it from the whole software and put it on the cloud. And this way, we don't need the reduce order model. And we can achieve better accuracy.
The APR model that you mentioned that you get after you work on
the APR, yes, it's an internal file that we use. It's not like an open source something. It's something that is proprietary in IS, but it can be translated into a file that is recognized by other software. Can be.
It's still like a physics-based model.
Yes, it's still a physics-based. Yes, but only works with our software. Okay. It has to be converted to another file to be able to work in open source.
The question is about privacy. How do you combine the cloud control analysis with the privacy concerns?
Yeah. So one solution is that this can be also on the edge computing, so it cannot leave the building. We can install, for example, a Raspberry Pi and have all this in the Raspberry Pi, and so no data leaves the building. That's one solution. The other one is we follow all the protocols, like we are following ISO 27001, GDPR, and we get consent forms for the building owner so that they know how we use their data. We have anonymization algorithm that is anonymizing the data we collect. And of course, in our API connections, we use like authentication, all the standard like privacy measures that exist. Basically, I hope I covered your question.
Okay, I just have a very small question. So you did the first implementation and early implementation in the Lande Rack facilities in Bologna, and then you are trying to replicate it in the other pilot sites.
So yeah,
this was part of the project development, or you already started it before the project?
It is a part of the project because we had. Because we recognize that our demo sites, we don't have any data. We have to go to the buildings and collect. So this takes time. So we wanted to speed up. So this way we found some buildings from our portfolios that we already have the data, so that we start immediately with the project. And one of these buildings was this facility from Schneider, where Schneider is a partner of the project and said, yes, I have this building, take the data and do your work. Yeah.
Was it planned already before the implementation of the project, or you arrived at the kickoff and then you found this problem?
Yes, we found this problem. We had to search internally in our companies to find suitable buildings that we can use the data. Yeah.
I think that's, we are done for this third part of our session. So keep connected, and we see each other at 11. Thank you very much. Welcome back to the session on artificial intelligence and digitalization. Now we go with our first speaker on the second session. Wait a second, so I can so that you can see us as well. Now you should be able to see us in a second. Anyway, right now it will be José Luis from Elracat, who will be our first speaker. So please get with us. Okay, let me see why it's not working again. Okay, ahora sí. Okay, now you can see us as well. So I think that we can start. Yeah, please, José Luis, you can come over here. I will share the screen for you, and then we are ready to start. Okay. Right.
To pass the slide like this, yeah? To go to the next slide? Okay. Okay, hello, my name is José Luis Castro Aguilar, and I will present iPredict. It's a predictive maintenance tool of the HVAC system using artificial intelligence. First, I will explain about me, about EURECAT, about the Sphere project, and then I will go more in detail about iPredict, the architecture, the Italian pilot, and the task and the initial results. About me, I have studies in engineering, and then I work on IT for many years, for more than 10 years in different countries. And then afterwards, I wanted to change career and to work in energy efficiency, and I did a PhD in Australia in energy efficiency in buildings and a lot of simulations. And then after I did a postdoc in the United States. And in the last years, I have been working as data scientist in energy efficiency in buildings, and now I'm a researcher at the Applied Artificial Intelligence unit at EURECAT. EURECAT is a technology center. It's a non-profit organization. It's based in Catalonia and is working on applied research and has different units working in sustainability and digital area. And yeah, they work the area in the sustainability. They have worked also in mathematical models. The Sphere project is funded by the European Commission, and the goal is to optimize the building life cycle and reduce cost and improve the energy efficiency in buildings. And it's composed by 17 partners. And well, it's a project that is finished in 2 months. iPredict is one of the software technologies in the Sphere project, and it focuses in the use and operation and maintenance of the building. It's a predictive maintenance tool of the HVAC equipment and using the real-time data and machine learning algorithms with the objective to reduce the loss of comfort and the loss of efficiency. iPredict creates a data-driven model using all this data from the sensors, from temperatures inside the building and set points and the operation status. Also the weather data from outside, solar radiation, temperatures outside, wind speed, and then the electricity, and the thermal energy consumption. So iPredict is doing the prediction of the energy consumption to detect the abnormal energy consumption in the heating and cooling systems. And if there is an abnormal energy consumption, send a notification to the facility manager and to the maintenance tool. The architecture, we have been working in the Italian pilot. So we are gathering all this with sensors and meters, gathering all this information, and all this data is sent to the platform. Also, we are gathering the weather data from a website. And then iPredict is doing the calculations, the prediction of the energy consumption based on the data, and calculating the deviation, the predicted between the real, and is sending all this information to the platform. If there is a deviation, then send to the alert and the notifications to the iMan application, that is the maintenance tools and the facility manager. The Italian pilot is a 3-story building in San Salvo. In the ground floor, there is an office. And then in each of the another floors, there is an apartment, 2 apartments per floor. Here we can see that the floor plans. This is the ground floor, the office that has 4 different areas. And this is the apartments that they have the living kitchen, and then bedroom, small studio. So there are 2 apartments for each floor. The HVAC system is composed by two systems. The heating system is radiant floors in the ground floor. Here you see radiant floors in the ground floor and in the second floor, and radiators in the first floor. This is for heating, and also there is a separate multi-split electric heat pump system for cooling. But they can also use for heating if the tenants they want to use it as well. And there are like one unit in every room. So we have like three. Here we have like for each apartment there are like 3 units. In total, there are 84 variables in the Italian pilot. So engineers from COMSA, they have worked in this implementation. We have, from outside, we only have outdoor temperature. So that's why we are gathering the information from a website like solar radiation, wind speed, and also as well outdoor temperature. And there are thermal meters for the heating system and electricity meters for the HVAC system. Then in each room, we are gathering temperature and relative humidity. This is for each of the rooms in each of the apartments. So we have 4 apartments, 1 office. Each apartment has 3 rooms, and the office has 4 separate places. And also in the ground floor and in the first floor, we have variables from the HVAC units. So we know the set point temperature, so the tenant, which temperature they set in the HVAC system, in the temperature as well, and the operation status to know when has been on or off, and the operation mode, if they are cooling, if they are heating, they're using dry, fan, or auto. We are gathering the information from wonderground.com, like this weather station is located 200 meters from the pilot. We are gathering like solar radiation, outdoor temperature, relative humidity, wind speed, so wind direction and barometric pressure. So we are gathering all this information from a weather station because we don't have a weather station in the pilot. The iPredict, the daily task. So iPredict is run daily, and first we downloaded all the data from the platform. So all the sensors and meters data have been sent to the platform. We downloaded all this data. We're doing cleaning the data, resample the data, filling gaps, and then upload it again to the platform. And then we are running the algorithms. So what we are doing is for yesterday, for the day before. So for yesterday, so we have all this data from many days. We have the inputs, like the temperatures inside the building, set points, the operation status, when it has been on or off, because in the office, normally they have for many hours, but in the apartments, they can switch on or switch off the air conditioner when they want. So with all this information, all these inputs, and the weather data from outside, and then the targets are the energy consumption. So we are training the algorithms. The algorithm is trained with all this data just to make the relationship between all these inputs and the energy consumption. And then for yesterday, we are doing the prediction. So we are predicting which is the energy consumption for yesterday with these inputs, with these temperatures outside, inside, and so on. And then, but we already know so the real energy consumption. So we calculate the deviation. In this example, so the estimated was 1.19 kilowatts hours. So what was the estimated? But the real was 1.46. So this is a deviation of 18%. So in that case, when the deviation is quite high, we send a notification to the facility manager. So that's the last part. Like all the results, all they are sent to the platform, the real consumption from yesterday, the predicted, and the deviation. And if the deviation is higher than expected, we send an email to the facility manager and to the iMan, that is a tool in the Sphere project, is a maintenance tool. and then the facility manager is able to analyze the more in detail the data and just to log a work order to see if there is any fault in the apartment. In this pilot, we have data from end of July this year. Unfortunately, we have only a few days of data. So we have some initial results with the data that we got. These results, there is in this apartment. So the algorithm was trained from the 1st of August and until the day of the prediction. So here there are like predictions from the 16th to the 31st of August. The blue one is the real energy consumption, and the orange is the predicted by the algorithm. And the dots are the deviation. So we have the green line is with 0% deviation, and the orange is 25, and the red is like 50. So the deviation is the algorithm didn't predict quite good. So in that cases where there is no energy consumption, this is the very low. Is the energy there was not energy consumption from this back system. So one of the apartments is empty, and it's always showing this little of consumption due to the logger and so on. So where we can see some of the results. Some of the days there were predictions that were quite okay. Some of them they were not 25%, or these ones, and this one 25. In that case, also we haven't done yet. But for example, if there is no energy consumption, maybe we can remove these days for the training, because it make a problem. So there's something we're working on. And also, we can see that some of the days they use air conditioning and some not. There is another apartment that they use more regularly the air conditioning. So we can see here, like most of the days they use the air conditioning, and again we see the real, and we compare with the predictions. In that case, they are better. Like there are some predictions that they are much better than the other one. So, but again, so we are training only from having days from August, and we still have more to improve the accuracy of the algorithm. So just the conclusion is that for the Sphere project, it was desired to have a predictive maintenance tool in this building digital team project. And this tool is following a data-driven approach. So it's using all this data that we have from sensors and uses all these machine learning algorithms just to make predictions of the energy consumption. And if detecting the abnormal energy consumption, then is sent or higher. So the real the energy consumption is higher than expected, is sending a notification to the facility manager and to the maintenance tool. So whether detecting the abnormal energy consumption also can save energy and reduce the CO2 emissions. And I will say that data-driven approaches, the models, they are becoming more important because we have more data. We will have more data in the future, more data available in the future. And also there is a progress in the sensors, in the Internet of Things sensors, and also progress in the machine learning algorithms. So there is a progress in all these areas, so that we may use more data-driven models in the future. So the results have been shown only, but we need to improve because we have only data from this month. So we have been working to get the results, and well, if we have more data, more days of data, more weeks, and then we can see we can have more data to train the algorithms to see all these relationships between all these inputs and all the energy consumption. That is, the algorithm is working. It's just to make this relationship. Also, something that we have to do is to do a better selection of all the variables of the variables that we have, to see which is the most relevant and for the for the algorithm to improve the accuracy of the algorithm, and also like the better selection of the machine learning algorithms. There are many ones that we can use. In that results, we were using like the support vector regressor, but there are many others that we would like to try, like artificial neural networks or Gaussian process or Gaussian mixture model, and there are more algorithms that we will try to see which one is better for this case. So yeah, thank you for your attention. If you have any questions.
Thank you very much. Are there any questions from the audience? I've seen that it seems that I didn't see the number of the slide, but that in the room in this room in which there are the consumption in HPC is more stable, the algorithm works better, right?
Yeah.
Deviation is minimum. While in the other in which there are more, it's more different. The algorithm doesn't look working so well until now. Why does it happen?
Well, because here is like something is to remove these days for the training, because this algorithm has not been switched on. So this day I think I should remove these days for the training, only the days that they have a minimum of energy consumption. And the second is like we have, because we are training from the 1st of August, so we could go back to see how many days they have been using their conditioning, and here we see that they use half of the day, so they have less days to train the algorithm. So that here, if you use regularly, so we assume that we have better data from the 1st of August. We have more days, and they are using.
But the algorithm is tailored for each of the room, or like the generalized algorithm that you use for?
No, it's for each of the apartments. Each of the apartments. Because there's something important is the user behavior. Like for example, if I can use for this apartment, I can use the data for this apartment and to make predictions for this, because there are other users, they will use more or less, or
what can you suggest in an apartment is not the same.
It will be difficult to have data from one apartment and to train the algorithm and to predict to another one. It could be, but it's more a challenge. So for now, we are doing just for the same apartment. So and to predict to the same.
I think that the objective as well was to detect when something was wrong. One machine is not working well, and each apartment, I think they have an individual system.
Yes.
For each one. So the idea is, not to use any details, but to detect if something is wrong. Somebody of maintenance has to go there to fix the machine. Because the experience is that one machine is not working well, it can be working in a bad way for years.
Yeah.
And nobody cares.
So nobody realizes.
Yeah, for now, like if there's a new apartment, the new apartment's a new system, so we assume that everything is working well, and we are trying to make the algorithms to test the accuracy of the algorithms, and one is implementing, and we see that the accuracy is quite good. Then is the point, like for the next years, then the algorithm is trained with all this data for all this, and then when there's something wrong, then we send a notification.
Another interesting point is that in this project, there was a problem with one of the partners with instrumentation. So there was a big delay running the site, but at least in August this year, they could perform the implementation, so the whole implementation of the fine. So even with the pandemic, partner with problems that they did the project, they still could do it. So it's when everything is okay, fantastic. But when there are problems, you are demonstrating really that you are compromising the project.
The more data you have, the more the algorithm. Okay.
Yeah.
Thank you very much. Okay, and now invite to stage Ryan. So please come here, and then we can just stop sharing. We're here. Okay, and then I put your presentation. It's the new one, right? Yes. Just see it. Okay. Perfect, Julian. The floor is yours.
Merci. So hello everyone, my name is Lurian Klein and I am a senior innovation developer at CleanWatts Digital that is based in Portugal, and I also have a PhD on sustainable energy systems. And today I want to present a paper here entitled Understanding the Role of Digitalization and Social Media on Energy Citizenship. And it's important to contextualize this paper a bit. It was developed under the Greta project, which is a Horizon 2020 project that aims not only to define the concept of energy citizenship, but also understand the best conditions for its emergence across Europe. So basically we have 6 different case studies that are very, very different in geographical terms, social demographic terms, very, very different preconditions. And on top of that, we have a very wide EU citizen multinational survey that is going to be spread across more than 10,000 citizens, European citizens. And I won't go through here like the main outcomes of the project, which is still rolling, but it's important to mention here that the Greta project was funded under that call on the last Horizon 2020 call on social sciences and humanities aspects of the clean energy transition. And in this call, the call is very specific. It aims to study the impact of digitalization and social media on the emergence and consolidation of energy citizenship. That is why we developed this work. So as a brief introduction to this topic also, the literature says that the digitalization of the energy domain and social media has the potential to boost the emergence of energy citizenship. However, this idea is premised on citizens being able to make sense of the energy information that is coming to them. Because of that, we decided to look at the role of digitalization and social media on energy citizenship by looking at it from an energy informatics and energy literacy perspective. Basically, by looking at that, we aim to understand how engaging with energy-related information may or may not support improved decision-making processes and, by consequence, the emergence of energy citizenship. And just to clarify here some key topics in this paper, energy informatics is how we use ICT to improve decision-making and the real-time use of energy. And when we talk about energy literacy, it's about people being able to make sense of information. So hence, the literature says, and we defended in our paper, that energy informatics and energy literacy play a significant role in spurring energy citizenship behaviors. And what were the methods that we decided to use in order to try to prove this hypothesis? So basically, we conducted interviews with our case studies to understand how citizens within these case studies currently use energy information and social media to communicate with others about energy-related topics. So we performed first interviews with them. Then we performed a social media content analysis to identify key energy-related topics that were being discussed in social media, namely Twitter. And then we also performed topic modeling on top of the interviews to identify common factors across the case studies related to the way that energy information is currently presented and represented within the case studies. So by doing that, this topic modeling, we tried to find the main gaps and the main good practices related to the presentation and representation of energy information.
Yeah, I didn't share it with the audience, so
they cannot
see it at the moment.
Sorry for interrupting. No problem. Okay.
Can you close this?
Yeah. Merci. Okay, we have it here. Apologies. No problem. Back on track. So we developed these 3 different methods to understand the role of digitalization and social media on the emergence of energy citizenship by looking at it from an energy literacy and energy informatics perspective. It's also quite important to talk here about the different case studies in the Greta project. So we developed a highly different case studies that are very different in social demographic, social technological, social political, institutional, and geographical preconditions in order to understand the best conditions in which energy citizenship can emerge. And just as illustration, for instance, in Portugal, we have a national renewable energy cooperative called Copernico, which spans across the entire country. But in Italy, we have a renewable energy district. So we are talking about the local level, which is the Bologna-Pilastro Roveri district in Bologna. We also have a virtual energy community in Germany, which is a virtual app for energy citizenship. So the members of this virtual community are the members of the app, using the app. We have like this transnational electrical mobility network that spans across different countries, and so on and so on. I won't go through all of them, but just so you know that the case studies differ very much between each other. And also they have here, you don't have to understand this very crazy picture, but this is just to say that energy citizenship in the end of the day is about the proactive engagement of people in the energy transition. And at the beginning of the project, each case study had, we defined different levels of engagement before the implementation of the project. And then we want to see at the end of the project and next year, how far the citizens moved up the engagement ladder, let's say. So we have different levels of engagement in the case studies also. So now I'm going to present you the results of each of these 3 methods that we implemented. So for the interview analysis, when we designed the interview, we wanted to seek information on, we wanted to ask information for citizens on why the green energy transition is important to them, what actions can be taken, and how they can get involved. So basically, this is how we structured the open-ended questions in the interviews. And the results that we got were those. So the main channels for dissemination of energy information across the case studies are flyers, interpersonal meetings, town hall meetings, newsletters and magazines, websites and blogs, social media, radio and TV, and energy management platforms or apps. And here it's what also came out of the interviews is that these channels of dissemination of energy information, they are very useful to advance energy citizenship behaviors because they give up-to-date information to citizens and also allows them to get more educated about their energy consumption and energy use in general. We also understood that these channels, they are only useful depending on the message that we are conveying and to whom we are conveying this message. So the messages must be tailored to different, let's say, end user segments. And also energy information, these dissemination channels, they help in visualizing energy information and circulating this up-to-date information. Okay, so for the second method, the results for the social media content analysis that I told you before, we analyzed trends in Twitter related to energy-related topics. So basically, we got the interviews, we got the key energy-related themes that were talked about in the interviews. And then we used these tool called, this is not the up-to-date PowerPoint presentation, but no problem. But then we used this tool called hashtag #FindMe in order to seek for these hashtags in an 8-week period, like the hashtags that are rolling in Twitter. And then we try to analyze the popularity of these hashtags in contrast with super popular hashtags on Twitter that are not related with energy. And okay, you don't also have to understand that, but the first graph, the graph on the top, are related with the energy-related hashtags that we looked for, and the popularity of these hashtags are very low in comparison with very popular hashtags. So what we understood from this analysis is that the hashtags do not generate a lot of engagement online on Twitter on energy-related topics that are they are usually there's no comments and really indeed no engagement, except in cases where like a celebrity just like Leonardo DiCaprio posts something about climate change and so on, then there's some sort of engagement. But in general lines, we understood that energy-related topics do not spur a lot of engagement online. And so because of that, we concluded that social media is not yet fully exploited, the potential of social media to inform citizens on energy-related matters, it's not being exploited in its full potential. And then because of that, we concluded two things, like different stakeholders, they have to start using more social media in order to engage in energy-related topics. But also whoever wants to use social media to engage people must start thinking about incentivizing like massive campaigns online and then like putting a lot of dissemination efforts in order to create some sort of momentum online and create some sort of popularity with these hashtags. And finally, with the third method that we used, which was topic modeling, basically what we did was, as I said before, we got the interviews and then we used this method called topic modeling to find key sentences within these interviews that were common across all case studies and understand what are the main gaps and what are the best practices related to the way that information is presented and represented to citizens within these case studies. And it's important also to make clear here that we follow this social constructionist perspective, meaning that there is no one universally valid answer to this exercise, because here we are dealing with uncertainty and multiple opinions, so it should be always open to different rounds of assessment. So the assessment that we performed in these interviews are only related to those interviews and those case studies. That was basically that. And this is actually quite interesting. So in terms of the main gaps that we saw across the case studies on how energy information is presented and represented, they said that information should more easy to use and it should have a more intuitive presentation. So it was all about the visualization of the energy information. And there should be also a simplification of overly complex technical jargon, so common folks can understand what we are talking about. These were the main ones, but we detected actually other different gaps. And in terms of good practices, like the most common one across the case studies was the humanization of processes. So it was using energy information to try to spur social value generation. And yeah, so with those answers, we understood that these gaps and these good practices, they could be very helpful to suggest potential, they could actually be translated into end-user engagement mechanisms that could be eventually embedded in like energy management platforms in the future. We can take this theory and try to then embed and create maybe some different end-user engagement mechanisms, gamification mechanisms that can be eventually embedded in these platforms. And then we also understood that it's fundamental for us to surpass these technical economic constructs and start looking at the more qualitative realm of the energy domain, because people really value the social dimension of energy information. And here, by concluding that, we say that this is related with the concept of corazonar proposed by Santos, which is like the warming up of reason. Basically, it's just like it's a nice term, which is basically we should start looking at the qualitative, more subjective aspects of the sharing and representation of energy information. So finally, in terms of the discussions of this paper, as I just explained, the interviews allowed us to identify that energy information should be made more easy to use and more intuitive, and we should reduce technical jargon as much as we can in order to touch every sort of every category of citizen possible within these communities. And in addition to being understandable, we also have to start taking into consideration the affective or the emotive aspects of information. And this aligns very well with our hypothesis in the beginning of aligning energy informatics and energy literacy, looking at digitalization and social media on the emergence of energy citizenship by looking at it from energy literacy and energy informatics, because energy literacy, this is not something that I mentioned before, but and I won't go through in details about that, but it has different dimensions, and you have the cognitive dimension, the affective dimension, and these are actually the most relevant ones in terms of energy literacy. And by analyzing our interviews, we understood that the affective dimension should be made as important as the cognitive dimension when we are talking about the presentation and representation of energy information. And we also understood that the socioeconomic conditions of our case studies also changed their information needs. So for instance, not all energy data, not all energy information is relevant to all different stakeholders. So for case studies that were not so affluent as others in economic conditions, the energy costs were more important to them than like these very affluent case studies. So we have also to know how to read the room. Let's say you have to actually personalize your speech when you are communicating about energy information to others. And in terms of social media, we understood social media as a tool to spur the emergence of energy citizenship. Well, social media has the potential of spreading misinformation, so we have to be a bit aware of that. There's also this generational gap in terms of using social media, so we must also understand that by using social media solely to try to communicate about energy-related topics, we are not addressing all sorts of stakeholders involved in the energy transition. And because of all of the results that we got from the analysis of the social media, we understood that the energy topics, the impact of the energy topics on Twitter at least, is not as strong as it could be so far. So then, as I said earlier, we have to start thinking about like promoting like massive campaigns in order to try to spur some engagement. And voila! This study, it was one deliverable of the Greta project, which is it was developed under the umbrella of the Greta project, and it is going to, the results that we got here are going to help us to further implement our case studies. and then support the creation of design principles for energy interfaces based on energy informatics. And this is what I had I had in mind to present.
Thank you very much. Sorry for the
Yeah, no problem, no problem.
Is there any question from the audience?
I have too many questions. I'll talk to you later.
Okay. Yeah.
We are working on energy community projects in which the bottom-up approach to convince the users to be part of the project and install smart meters or panels, etc. is one of the most challenging ones.
Exactly.
And keep them engaged, etc. So, but I mean, maybe some small question that is related to the fact of why you choose Twitter as an analysis tool and not like or it can be Facebook or Instagram.
I guess it was a matter. This specific method was developed by LUT, which is our partner in the consortium. So it was not developed by CleanWatt Digital, but I understand that it's because we analyzed all methods in which we could analyze social media, and this #fi.me was a very useful tool that allows us to use that. So it was more based on convenience of having available methods to analyze social media. And also, of course, you have timelines, you have some sort of deliverables to deliver in time. We wanted to analyze a very wide plethora of social media, but then we just focused on that because then there was an easy method to analyze that, and that was it.
Yeah, I just commented on that actually about Twitter, because if you had such results in Twitter, which is already kind of intellectually more upper class than other social media, but the results would be another platform. So already Twitter users feel that the information is too complicated. There's a lot of room for
I'm not even on Twitter. That's the thing. And for this method specifically, because the interviews and the topic modeling, sorry, I understand that you have a question. Just let me just address this comment. But we performed 3 methods, but the social media content analysis was performed, and it was not focused on the case study, so it was also very broad. So the interviews were related with the case study participants, also the topic modeling to understand the gaps and best practices related to the presentation of information was also focused on the case studies, but the Twitter was just a broad analysis on Twitter in general across the world.
This is perhaps a question, but do you have any experience or do you find any difference between communities in big cities and small communities in rural areas? That is one question, because I think the social structure is quite different. And the second is the pressure we have today in the news about energy concerns is huge. But they are a totally different problem than the implementation of a small energy community. So it's like the people somehow can be in a virtual world of non-reality just because they are receiving messages from TV about problems, for example, with Russia, with gas, and those problems they don't affect at all. And in the opposite side, they should be implementing charging stations for electrical cars, and they do not. So did you find any situation?
Yeah, these are actually very interesting comments. So maybe I can talk a bit about Greta, but then I can just expand the comment and then talk about my work in general, because I work with renewable energy communities. So in the Greta project, the dissemination channels, they were already in place. So it's not something that the project designed and implemented in a very structured and standardized way in all case studies. So for instance, I can take the example of Portugal, because Clean What's Digital is based in Portugal, and I am running the case study in Portugal. It's this national renewable energy cooperative, and their dissemination channel is hyper personalized to the members. And if you see this engagement level, they were categorized as already very active, and they are just like moving towards being everyone being advocate of the green energy transition. But many members are already in that level. So the case studies that we have, the 6 case studies that we have here, they are very specific in terms of their level of engagement. But what we understood is that whoever is, because, okay, we represent a project consortium, the Greta, and we interact with the case studies through gatekeepers, right? Whoever is like the director of the cooperative in Portugal, or like the town hall representative in Bologna for the district in Bologna. So they already have all of their tools rolling for communicating with these people. So I do agree with you that if someone is just stuck like on a TV channel and just getting very generic information on climate change and everything, it's quite hard for them to understand, okay, how can I do something to have an impact, or to get engaged, or to be like an energy citizen in the end of the day, because this is about energy citizenship. So it's all about tailoring these dissemination channels and the information also, one thing that, and then going a bit out of the Greta project, but in Portugal, even before the transposition of the EU directive on renewable energy communities, we developed the first renewable energy community pilots in the country, years before the transposition of the directive. And I worked with highly remote villages in the middle of nowhere, really, in Portugal. And what we understood is that once you have a group of people, even though you are in a very homogeneous setting, okay, I'm talking about a village in the mountains up north, even though they look homogeneous, it's quite important to even categorize these people in different levels of engagement. We even developed an entire framework for end-user engagement related to peer-to-peer energy sharing, because then you understand how effective you can be. Some people, regardless how much information you give them, they are just not very willing to partake in the energy transition. So regardless what you do, you cannot move them in any way. So if you understand that from the beginning, you can like derive your efforts to those people that are willing to participate or are very proactive already. Those that are super proactive, you don't actually have to do much. It's just like sharing some information. Okay, they are already like front runners. Things are rolling. But then there's people, I understand that I have to leave, but then there's people that are also willing to participate, but there's some sort of barriers that block them from participating. And then you can deviate your efforts and then really like optimize your focus on end user engagement strategies and tailor specific strategies for different segments of end users. And then you can be very effective. So it's a plethora really of things, segmenting end users, personalizing the communication, creating different channels of communication. And then that's basically it. It's putting a lot of effort on how you deliver the info.
Thank you very much.
Thank you. Thank you, everyone.
Okay, now we have the 7th presentation of the session. Okay, so I invite Luc to join me with a very interesting paper presentation on smart metering and low voltage network digitalization solution in Burkina Faso, because I'm not able to read the name, but it will be very interesting to see what you have prepared. Thank you, Luc.
Thank you. The screen is being shared.
Thank you for asking me, but yes.
Yeah, perfect. Okay, very good. So hello everyone, I'm Luc Richaud. I'm a project manager for Odit-e, a French-based company in Grenoble, in the Alps. And I'll present today the project Africit-e and what we did in this project. yeah, I will try to do not be too overly technical as was explained before, but this is quite smart grid, so it requires some technicality still. Just a quick sum up of the project itself. The funding body is the French government, and the beneficiary is the Sonabel. Sonabel is the DSO and energy company of Burkina Faso. The consortium is led by the Smart Grid Institute that is based in Lyon in France, and 3 others SMEs in French SMEs, so Odit-e in Grenoble, SmartSide Paris, and Grid Pocket that is actually of the region, Sophia Antipolis, so really close to Nice. And we have, well, a replicability board with many industrial and academic partners. So the project itself is based in the suburb of Ouagadougou, the capital city, in a neighborhood called Azimo-Ouaga 3000. It got more or less 800 inhabitants, but there are some. It's mainly residential, but there are some shops as well, some hotel, fish shops, mosque, some restaurants. So there are different type of energy users, and we deployed there 500 smart meters on a PLC technology with 4 data concentrator units, the associated hidden system to be able to communicate with us with the hardware, some analytics solution that will be the digitizing part of the project, and a mobile app to provide consumer with consumption information. So that I think it's on this part that we will be linked with the previous presentation, but how to communicate with end users on their needs, on their consumer consumption habits. Yeah, I'll just explain quickly the architecture. So we have the smart meters that are based the customer premises, the data concentrator units that are in the secondary substation, communicating with the hidden system, which is the smart site software, and then analytics and the mobile app just under. And the whole use case, the whole point of this project was to use flexibilities, the consumer flexibilities, in order to reduce the congestion that can happen on the low voltage network. And so this requires a lot of involvement from the end user. And how we did that is that so we have the smart meters deployed. We collect all the data from those smart meters. We communicate with the end user via the customer app. So the end user get the bills done automatically, and they have a monitoring of their consumption on the app. And through the analytics, we model the network in order to forecast congestion, to inform the customer accordingly, and to distribute among the customers the available capacity. So let's say there is one part of the low voltage network that is under constraint, so one feeder. We estimate that there will be a consumption of 200 amps, like a current of 200 amps, too high on top of the nominal value. So we will reduce the power the customer can consume by this amount in order to do not have such congestion. And so we send back an order to the smart meter to reduce this maximum power available in order to do not have the congestion happening on the network. So now I'll try to present each of the components. So the hidden system, smart metering and hidden system, the analytics and the customer app. So starting with the smart metering and hidden system. So as I mentioned earlier, we have those smart meters deployed at premises, at the customer premises, then the data concentrator units in the MVLV substations, and and everything is sent to the hosting and control center that is hosted by the DSO, so the Sonabel DSO in this case. And so those equipment have been deployed, and something worth mentioning, because this is the first smart metering project in Burkina Faso, and for residential use, there is really few smart meters deployed at Africa level, and we had no main difficulties for the deployment of the equipment itself. 90% of all the equipment was deployed in 3 months, which was in line with the project planning. So we were expecting much more difficulties. Then from this architecture, we have some requirements of data. So from the lighter to the more to the heavier requirement in terms of load on the metering infrastructure. First, we want to have billing purposes, which is the main objective of smart metering. Then for the mobile app, we needed the monthly active energy index just to communicate the invoice to the customer. But we wanted as well to have the daily load curves, so we can communicate it to the customer and they can see, am I consuming as I'm used to? Is there any difference with my previous patterns, etc.? And then for the analytics solution, we needed the daily load curves and daily voltage profile as well, in order to compute the model of the network. And this was the challenging part, let's say, because it was a bit too much for the whole smart metering infrastructure. So what are, at the end, the difficulties we encountered? So we started the project really optimistic, thinking we would be able to collect all the data we needed. So we actually failed in an all-in strategy. Like we set up all the smart meters with a data collection that was 100% of the data requirements, and we end up with a really few data. The data collection rate was super low. So we had to reduce the load to maintain critical functionalities. So the billing, which is the most important for the to determine what was the causes of this low data collection rate. So it was many low noises, many low noise sources on the PLC network. So all the equipment that are in all the hardware, how do you call that? Sorry, all the washing machine and things they have in the houses are not following the same requirement, the same norms as the EC norm, for instance. So we had a lot of noise on the PLC network. So that was creating a lot of power line route restorations. So the smart meters were not communicated as they should. They were always changing the route to try to get the information to the data concentrator units. And the good thing that there were no or few major noise sources on the PLC network. So we could it was not necessary to deploy filters in order to isolate those major noise sources. And thanks to that, we identified some software improvements, a number of hopes, an increased number of hopes. So the communication between smart meters were increased by 8 to 10 hops in order to reach smart meters that were further in the network. Optimized call in PLC network and the establishment strategy of route was changed. And after that, we had the collection rate for the invoicing part that was 96% for the 3 last month. So we were good for all the critical functionality, let's say. And here is an overview of all the smart meters deployed on the demonstration site. Within green, the data freshness means it's on time. and we have few smart meters that are in yellow, orange, or purple, meaning they are either disconnected or they have difficulties to communicate. And so thanks to this smart metering infrastructure, there were two different use cases: the billing and bill collection. So we set up the monthly billing at a fixed rate. This is something that may look classic. I mean, because we're in Europe, we're quite used to this kind of functionalities. But this was the first for the DSO. So the billing was performed at a fixed rate, which is a great value for consumers, because they have sometimes the statement of the meter is done on the 1st of the month, sometime on the 10th, sometime on the 15th, meaning from one month to another, the customer could pay 20% more or 40% less, and they had instability in their bills, which was making a lot of difficulties on actually paying the bill and recovering the bill for the energy company. And having this made at a fixed date without delays improved the working capital requirement for the energy company, which is something they really need to keep developing and to keep bringing electricity to new consumers. Another functionality, let's say, they used is the ability to remotely disconnect in case of unpaid bill, because they have consumers that are just keeping consuming without coming at the office to pay the bill, because they have to go to the office to pay it. And usually they send someone to disconnect the meter, but of course, sending someone disconnecting the meter creates, some arguments with the customers, and so with this system they can remotely disconnect the consumer, so they can come and pay the bill. And a functionality of public lighting, fully automated, was deployed as well. So all the smart metering infrastructure can be used without additional cost to switch on and off the public lighting. Then the second component, the LV network. 5 minutes more. Okay, good. LV network digitization solutions. So there were first a network analysis that was performed. So as I said, for this component, we needed the load curve and the voltage profile, and it was not available everywhere. So we could perform it on three different secondary substations. So this is Odit-e work, and based on this data, we retrieve the topology of the network. So which smart meter is connected to which phase, to which feeder, and which secondary substation. And based on that, we aggregate all the loads of the customers, and we see if there is one feeder or one phase that is overloaded. And if yes, we can explain to Sonabel how to rebalance the network, make sure that there is not one phase that is having all the loads of all the customer loads and the other being empty. So this is for the load in the middle, and here it's for the voltage. So we can see they have troubles in voltage. They have a really high range of change. So we have the 230 plus minus 10% in here, and they go above the 230 plus 10% and below it as well. This mainly because of imbalance in the network. And then we provide them as well with a PV insertion capacity and simulation tool. So this is based on the previous model. We explain this software gives the information about how much PV panels can be implemented at one given smart meter without creating any voltage issues or additional voltage issues on the network. And allows to simulate what would be the impact of one new installation on all the remaining capacities. This part was mainly for lobbying for photovoltaic energy, because for the moment in Burkina Faso, there is no net metering possibilities, so people can't self-consume photovoltaic energy, and there is no feed-in tariff either. So it's for the moment people can't install PV panels, but in case they could, this would be a useful tool for Sonabel. And finally, the power limitations. So based on the forecast, we reduced the power that is available at customer premises in order to avoid congestions. And this is the information that is provided to Sonabel. They can refuse the planning we are giving to them in case they disagree with our analysis. But they have the ability to make us not act on the customer smart meter. Okay, so just quickly, I'll go to the mobile app. I think so. This was interesting for Sonabel for the topology identification because they had no clue about which customer is connected to which secondary substation. So that provided them with a new information in the GIS. For the load and imbalances analysis, mainly because it has an impact on the voltage issues, and they have a lot of under voltage customer supplied with too low voltage. Some reserve regarding PV, as I said, no legal framework for net metering and feed-in tariff for the moment. And requirement for rollout, this is something we see often, is that everything needs to be on-premise infrastructure, or no cloud solution, that they don't really appreciate cloud solutions. And I finish with the mobile app, and I'm good after that. The mobile app, some screens, some connection screen, a bill estimate stating, okay, so far you're going to pay this amount, considering the tariff that is the national tariff that is available. The consumption monitoring by day, weeks, month, and years, and the expected power limitation. So the schedule. The planning that we send to Sonabel is sent as well to the customer, so they have an idea about when the power will be limited because of a congestion, and they can set their life accordingly. So they can change the time they are expecting to do a certain activity that is energy intensive or things like that, and some energy saving advices. Some feedback about this mobile app. It's interesting for the customers for improving their satisfaction, because they can understand better how to act on their energy consumption, to promote some energy saving practices. The bill estimate is something that was appreciated because they can have a look about how much they are going to be charged at the end of the month, because they are charged on the monthly on the real amount of energy, and the notification for expected power limitations, so they can act accordingly and not suffer from the outages, because often there is just an outage and they just don't have power. So it's better to have a reduced amount of power rather than nothing. Feedback. So basically, half of the people activated the account of the mobile app. Which is, I think, quite a good. I would have liked to have the opinion of the previous speaker, but I think it's quite a good amount. And some testimony, where people do it out of curiosity to evaluate the level of consumption, and someone told us, I want to know how much it costs me to use the air conditioning one day. So I will use that in order to calculate what the price of 1 day of air conditioning, because for the moment I'm using it, but I have no clue about how much it costs me. Good. Just what's next? This was the Africit-e project, and we are going to use this demonstration site into the Eureka project, which is a LIPRI financed by the European Commission. to engage customers into something that is more automated on their side, to automatically reduce the consumption in case of congestion, and to broaden the LV network analysis. That's all for me. I hope I haven't been too long.
Thank you, Luc.
Thank you.
Are there any questions for the others? Maybe just one.
Okay.
No, I have, but I did all the first questions. So please.
Okay. You mentioned that you had problems sending the information to the network.
Yeah.
I mean, you were using physical cable for the smart meter.
Yeah.
And you had problems with that.
We use PLC, so it's using the electrical network. It's so the power line communication. So the smart meters is sending the information through the electrical network. And when you have if you have bad appliances, like not good quality appliances, they create some noise on the band, the frequency band, where this is where the smart meter communicates. And so if you have an appliance that is creating noise on this, it's Senelec A band, the information the smart meter is sending is mixed with the noise, and then the data concentrator units can't retrieve the information from the signal.
Can you use filter or something like that for that?
Yeah.
That noise?
You can use filter to so you have the house of the consumer, then you can put a filter between the house and the smart meter in order to just isolate the problem that is in the house, and then you have the smart meters that can communicate with a clear signal. The problem is the filter itself is quite expensive. It's like 50, 60 euros. So that's double the price of a smart meter rollout, because a smart meter is basically 50, 60 euros as well. And it consumes energy as well.
GSM is not affordable as well. I mean, to connect VR radio, or would be more expensive.
GSM is not really an option for what I saw for the moment in deploying smart meters in Africa. Is not really an option for massive rollout, because the OPEX is important. You have to pay every single SIM card, and if you have a customer that is consuming 500 kilowatt hour, and you end up paying more communication fee than the bill of the customer itself, it doesn't make much sense. So they have GSM smart meters for the big consumers, but for a massive residential rollout, I think the PLC is more adapted.
Thank you, Luc.
Thank you.
Okay, we pass to the last presentation of the day. Invite Andrea on stage. Just take this. Okay. Should have it here. That was an untitled, no? Ah, ti serve? Sì. Ci serve questo, ok. Please, Andrea, go ahead.
Okay, let's see if it works. No?
Maybe it's not working. Nothing there. Or you can remove this one.
No.
Okay. Try now. Still don't like it. You have to turn it on as well. This is weird, because it was working with the other USB, so it should work also with this one.
No, maybe it's a problem of the battery.
you want, I can just stay here. And...
No, I will manage. Yes, I think so. Okay, let's do it in a manual way. Okay, so first of all, I want to thank you. I want to thank R2M for hosting us and for organizing this event, this conference. I will try to be as brief as possible since we are a little bit late. I'm Andrea Perego from one team. I'm a management engineer, and I will talk to you about ECOFACT. ECOFACT is an Horizon 2020 project. ECOFACT, the acronym stands for Eco-Innovative Energy Factory Management System. But let's first have a look at the agenda of the presentation. So I will start with a brief introduction of the company. Then we will focus on the project overview. So I will tell you about the targets, the consortium, the demo sites, and the platform overview that will be the core of the presentation, actually. So the third part of the presentation, it will focus on the solution, on the digital twin platform. We will deep dive on that. And finally, we will focus on the next steps. So what's next, which will be the future challenges and possible call to action. Okay, so let's start with the introduction of our company. I hope it's not too loud. Okay, so we are a consulting company with more than 25 years of experience. We basically work in this field. So we work in the IC sector. We do provide end-to-end solution for our customers. So we talk about building information modeling, especially. We do work also in the manufacturing sector. This project is the scope of this project is manufacturing, actually, of the ECOFACT project, and we also work with the GIS solution, so with the GIS market. Okay, these are our key numbers. I will just be very brief. So we have a staff of about 100 employees. We manage more than 60K users. This is our total revenue, and we have 10 locations spread all over South Europe. So as one team, we always let's say that the sustainability has always been in our DNA. As a matter of fact, the logo of the company resembles the Earth, and our motto is to transform technologies and skills into value. And let's say that we want to do it in order also to create a better world using digitalization. That's why we took part to those projects. Those Horizon 2020 projects. So basically, we have applied for 4 projects within the Horizon 2020 program. Unfortunately, we have won only 3 of them, but let's say that they are very important for us, and we are very proud of working with this consortium. So basically, our role within this project is to develop the digital twin platform where the digital twin are hosted, where the BIM model, the digital twin are hosted. And then depending on the different project, we develop other applications, GIS, virtual reality, augmented reality. So we will focus on ECOFACT. Today is the only project focused in manufacturing, because the other projects are focused in building. So as you can see also from the acronym, so BIM4EB, BIMREL is not an Horizon 2020, it's the only one, and Infinite are focused on the building sector, while ECOFACT, as I just said, is focused on the manufacturing sector. Okay, so let's talk about the ECOFACT
project. So first of all, I want to underline one important fact. We are halfway, so we are just at month 24, so there are other 2 years ahead. So you will see some results of the project, but not the definitive results, actually. So the project is, as I said, is a Horizon 2020 project with a 12 million euros budget. It started in 2020. It lasts 48 months, and this, the work is carried out by a consortium of about 20 organizations. And the focus of the project, at least from our side, is the digital twin platform that will act as an energy resource management system. So what about, let's focus on the consortium. There are 20 partners, as I already said, from 7 different countries, 5 research institutions, 8 large industries, 5 small, medium enterprise. We are one of them, and 2 associations across the manufacturing environment. The scientific technological objectives, as all the, let's say, Horizon 2020 projects are specifically predefined. I want to focus especially on the scientific and technological objective number 2. So in this case, with the ECOFACT project, with the platform that will be developed within the ECOFACT project, we want to cut on the factory energy bill by an average of 25%. It's, I think, an important target, also considering from one side the situation we are all living, so the energy cost, and also from the other side, the sustainability. So what this could mean in terms of saving in CO2 emissions. I want to mention also the scientific and technological objective in number 3. So we want also to better control the environmental signature of manufacturing processes and supply chain. So our target is to reduce, thanks to life cycle costing and life cycle analysis approach, to reduce environmental footprint of manufacturing processes by an average of 4-8%. Alongside these specific objectives, there are other more general ones. So basically, the final aim of the project is to develop a platform, and we will see some screenshot of the platform that is, as I said, is work in progress. We will develop the platform reaching TRL 7. I think that everybody in this room know what TRL means, so technological readiness level. Alongside these scientific technological objectives, there are also non-technological objectives related to dissemination and exploitation. Okay, so let's focus on the real protagonists of this project. There are the factories themselves. First of all, I want to state one important thing. We wanted to test the solution on different industrial environments. So we have 2 demo sites related to discrete manufacturing, and we have other 2 demo sites related to continuous manufacturing. As far as concerned the discrete manufacturing demo sites, we have Arcelic, that is a factory of washing machine in Romania. We have Tofaş, which is a factory which is an automotive factory in Turkey, is a part of the Stellantis group. As far as concerned the continuous manufacturing demo sites, we have Athenian Brewery, which is a factory of beer, so it's a brewery in Thessaloniki, so in Greece. Goulion is one of the largest factory of biscuits in Europe, and is located in Spain. So basically, which will be the architecture of the solution we are developing? We start from the demo sites. We start from the field. So we will collect data from the field, leveraging from one side the existing protocols already in place in the factory. So taking data from the PLC, the existing sensors, etc. And from the other side, implementing a new infrastructure, so a new IoT infrastructure to get specific data. We will convey this data to a centralized data broker that is a solution made on Kafka. And this data broker will distribute, will convey the data to the higher level of the solution, so to the application level. And from one side, we have the energy and resource management system, so the digital twin platform. We will deep dive on that at a later stage. And from the other side, we have the dynamic LCA, LCCA supply collaboration services. So the combination of these two components will make up the holistic decision support system. So the ECOFACT platform itself that will help the final user to take the right decision and to organize the production in a most energy and cost efficient way. Okay, so let's recap very briefly the four milestones of the ECOFACT platform. So we have local data from one side, so we will take the data from the field thanks to IoT infrastructure that we will put in place and leveraging existing, as I said before, PLC, SCADA, actuator, sensors, etc. We will use the data broker to distribute, to convey, to clean, harmonize, and distribute the data to the different applications and services. And then we have, let's say, at the later stage, the holistic DSS that, as I mentioned before, is based by the digital twin platform that will operate as an energy and resource management system, and supply chain and LCA, LCCA services from the other side made on CIMA Pro. Finally, but very important, but it's also very important, we have the user interface. So from one side, the user will be able to interact with the platform to take the right decision. And from the other side, it will be able to access historical data or real-time data directly, having access to the platform. But let's deep dive now on the platform itself. So at least on the energy and resource management system part. So the digital twin platform is made basically by these three components. So from one side we have the digital twins themselves, so the 3D models with all the relevant documents, the relevant information, the data and metadata related to the models. That these 3D models have been modeled with Autodesk Inventor. From the other side, we have the application and services connected to, integrated with the platform. So we will focus especially on one of them, that is Optimis, because it's the more mature one, but there are other application and services integrated in the platform. We will see at a later stage. And finally, there is a data exchange layer. So we have different APIs that are useful to exchange data with the data broker and with the other applications. Okay, so these are, let's say, the digital twin host in the digital twin platform. But let's see directly the digital twin platform itself. So this is the user interface. So you can access on the left side different information. You have different label. So from one side you have specific information related to the demo site, documents, 3D models, and from the other side you can access the tool part. So you can have access to the different tool. One of them is Optimis, as I already mentioned before, to do the different simulation. So here you see a video representing the digital twin platform. So as you can see, you can have access to different information. Then you have directly from the platform access to the model, and on the model you can let's say that the real-time data, real-time sensor data are directly displayed. So basically, you can have access from one side to the data related to the different part of the asset itself, and from the other side, as you can see from the slide, and from the other side, you can also have access to real-time data, as I already said, necessary to do the different simulation. Okay, so let me just move on a little bit. So you can see also the historical data in the graph, and from the other side, sorry, you can also see always in a graphical way directly from the digital twin platform the real-time data displayed directly on the platform itself. Okay, so let's move on, and as I said before, let's focus on the first application we have integrated within the platform. That is, as is written, is an industrial energy flexibility and optimized management of generation asset application. It's called Optimis. Okay, so very briefly, how it works. So this application actually minimizes the changeover times, and thanks to the minimization of the changeover times, the final user can redefine the production scheduling. We already tested this application in the Athenian Brewery demo site, and it's been very interesting because we already have an important result, because the bottleneck span has been reduced by 20%, so it's a huge saving. As you can see, it's 20-hour saving. And also this result, I will show you the next slide, always could be translated in saving of other kind. So from one side, specifically, we wanted to underline that this lead to CO2 emission reduction of 16%. If we remember the initial scientific and technological object, this is pretty aligned with what we stated at the beginning. So, but as I say, we are only halfway, so we expect to have other results also in the other demo site in the near future. This is just an example of how it works. So you have to put input data, so about the cost, the actual production, and then the algorithm will run and give you results first in a Excel format, but then you can see the results directly in the platform itself, and also you can visualize the different results displayed directly on the digital twin itself in a graphical way. Okay, so what's next? So as I already said many times, we are only halfway, so there are many things we need to do still. So we have to integrate, let's say that it's work in progress, so it's not that we haven't to do it yet, but we have to complete the integration of the other application and services within the digital twin platform. So we talk about especially material flow simulation application based on Siemens plant simulation tool. We talked about a production optimization tool based on Gurobi solver. We talk about energy simulation for dynamic operation management and cost optimization. So basically, we will implement and integrate predictive maintenance model, starting from the data collection from the sensors and from the SCADA system, then developing an energy simulation, developing energy simulation algorithms to forecast abnormal behavior, and as I said before, arriving to a predictive, defining a predictive maintenance model in order to optimize and help operation and maintenance tasks. Okay, another tool we will integrate in the platform is the industrial energy disaggregation. We will do industrial energy disaggregation by products. So this application will help us help the factory to understand the consumption of energy related to the different product, and this will be very useful for let's say reshaping the production accordingly. And the last thing we will need to do is to integrate all the different results of the different application and services within the energy and resource management system first, but then integrate SCA, also dynamic SCA and SCCA and supply collaboration services within the overall ECOFACT platform. As I said before, defining how the holistic decision support system will be made and how will be able to support the final user. Okay, we are arrived at the conclusion of the presentation. So basically, since ECOFACT is a work in progress project, sorry, we are looking for other demo sites for the exploitation part. It stated that we could look for other 5 demo sites where to test our solution, our platform. And since, as I said before, the final aim of the ECOFACT project financed by the European Union is to reach TRL 7, so technology readiness 7. It will be also needed from our side to understand and to proceed after that, because we want to reach the full marketability of the solution. As you can see, there are already relevant results by 2028 or 2030, so to reach TRL, technology readiness level 9. Okay, so if you are interested in the project, please follow us. We have LinkedIn, Twitter, YouTube, we have a newsletter, or if you have any specific answer, please drop me a line. I wanted to finish with this quote because I think we are all in the same boat. This is a way of saying in Italian. I don't know if it works in other countries, but so we are all in the same boat. We do research. We do research and innovation, and it's tough. It's a tough job because starting from a white paper is not easy. But I think that when you start to see some result, it's very satisfactory. So the final quote of our presentation is: "Do not go where the path may lead. Go instead where there is no path, and leave a trail." Thank you very much.